We just heard, I'm really glad Doug's talk happened before my talk because I saw that safety was really important in his talk. And now that we are talking about autonomous systems, um, at APL we have been doing autonomous systems for quite a long time. One of the chart will tell you more about it. But the sponsors are wondering what real guarantee do they have about these systems that they won't do something really bad in the field? And this particular program came out of that concern. So we call it TESS. It really means safe. How can we even test these autonomous systems safely so they don't crash on somebody while testing and things like that? So safe testing of autonomy in complex interactive environments, that was the name of this program. So the outline of my talk is what are the needs and challenges for testing and evaluation of an autonomous system. I'll give you some background and definitions of some acronyms that we will use. It's an effort in test range management control system control department of test and evaluation under ONR, Office of Naval Research. And what is our forward thinking path of how we are going to test this, and a little bit overview about what we have done so far, and a summary. So unmanned systems they usually require an operator in the loop, and if you follow this flow of this arrows here, there is something operating autonomously. The decisions are, the sensors on the UXV or UAVs are sensing something. They're sending data to the operator. It could be that the operator is directly controlling the next commands that are going to the UAV, or it could be more autonomous in its own, making the decisions about how to get to the end point or how to take over the do a particular mission. So there are three different groups. Somewhat we break those into. One is a teleoperator, or an automatic vehicle, which does certain things like maintaining the camera angle or something like that, or an autonomous vehicle where you define the mission goal and let the software running on the vehicle take charge. And that's what APL has been doing. Has done many demonstrations of a particular flavor of mission level autonomy, where in a nutshell, we assign, basically it's based on a potential field, and you try to get to the lowest potential to find a solution for the problem that you're solving for. And that has been used on UAVs, air vehicles, as well as submarine vehicles, as well as ground vehicles. So now is the time to build a framework where we can test these things. And you can see it has been used in the past on some of the like the examples that I gave you. Let me show you. So this is what you don't want to happen. Right? So you want them to achieve you want these machines to achieve the objectives that you have set them for, but you don't want to have any unacceptable, unsafe behavior towards, first of all, us human beings, and even within themselves. You don't want them to collide against each other or things like that. So you need to define those buffers or that behavior some way, and some way to test that behavior. APL has been doing individual test, individual systems testing. And you can see they built a really small beast here. They called it Beast in way back 1960 something, 62 or something like that. And since then, there have been software for Predator, UAVs, some unmanned surface vehicles, and there has been autonomy on spacecrafts that you know, and including New Horizons and things like that. There came a time where the operators, so in 2004, we did a swarming unmanned vehicle experiment where multiple UAVs searched, patrolled, and tracked. Those are 3 different operations. They did that against whatever was on the ground. So these were the ground vehicles, and there were UAVs like this. That was pretty successful, and it was kind of a test run for bigger vehicles. So then recently, and I will go deeper into that later, but the focus shifted into building, the focus is shifting into building the test framework for these kind of vehicles. So the needs are, as we identified for this program, are build an infrastructure for safe and live testing. Live meaning the vehicles could be taking their own decisions, or a person could be driving those vehicles. Demonstrate live, virtual, and constructive methods for doing those tests. Those should be those methods that we demonstrate should be based on a particular network architecture called as TINA, which is how the Army ranges are connected with each other. And we believe that all these 3 things were not demonstrated before. Those would be the needs and the challenges that we took upon, where provide an infrastructure for safe testing of autonomous vehicles which can perform unpredictable actions. So we had to introduce faults basically, purposefully in there, or unexpected behavior, and show that under all circumstances they can be controlled by the range manager who kind of has a panic button in front of him, says stop right now, and everything should stop. So in terms of the key focus was on what is the capability that we want to deliver. Essentially, there is a system under test that you are trying to prove its autonomy is behaving the way you want it to be behaving, and that our architecture's level, technology readiness level, should go from let's say 4 to 6 or something like that. That was the main goal. That we are ready for going on a physical army range or military range and prove that to the test manager or range manager. And the relevance was that if these ranges are connected by a network where you are flying one UAV on one range, another UAV on another range, and you're exchanging data across the ranges, across the network, then you should be able to show that they are not going to collide into each other. Just because each of these vehicle could be $1 million vehicle, right? You don't want them to put next to each other and then watch them collide or not collide, right? And the cost benefits are obviously that you get to play with the real thing, but not let them. The tests are not destructive. So this is the architecture that we developed. I'll I won't be able to go too deep into it, but essentially we broke down. As you can see, the architecture is color coded. The top, I'm sorry, the top blue color shows you what was done for year 1 or 2. This is a 3-year program, and what is expected to be done in year 3 is in this white color, which I believe is just this white box monitoring of the autonomy, meaning you get to see why the autonomy is making those decisions. So in terms of layers, the top part, this horizontal line divides between the flight software versus the ground software part. The blue that got put in here, so we thought about it, and we put basically a hardware-based control on top of the SUT or system under test autopilot program. And we tried to get into the basic control of the sensor and the measurements and things like that. So if the SUT is here, system under test is here, then based on these arrows, you can see that the sensor measurements are coming down all the way to the ground, where they are getting manipulated the way you want the test to be manipulating those. They go back up, go through the stimulator, which changes those further if they need to be changed in real time, and then they go back to the kind of you're spoofing the sensors either in hard real time, or you're spoofing them at semi-real time. That's what the main goal of this architecture. And on the ground side, to be able to exchange data with other ranges, there was we have put in basically a virtual force generator, virtual elements basically that you can control from the ground, and you can pretend that those are being seen by the UAV or whatever is up, whatever system that you're testing. So these are the photos for the payload that was put in on a that will go on a Boeing Scan Eagle probably in about a couple of months. And it has been used before too. And we used the wireless network cards from a company called as Persistent Systems. Their wave relay cards were used in this. And here, and the tests, there are, as you see, there are two boards here. One is, this is the autopilot that comes with the UAV, the bottom one. The top one is just a gum stick that was running the test program's control loop basically, which could take away the control from the autopilot of the UAV and take over if it is behaving unexpectedly. So the team did this, as you can see, right in the middle of the winter. And it proved pretty well. I'm going to show you some more photos about how it looked. So the shaded area is the buffer area in where, okay, so the green, so when you have your UAV, you want to have it, if the test fails, what should it do? It should come back to a safe point somewhere. That's the green area. The UAV itself is blue, and it's following the target here, the yellow target here. But there are certain areas it is not supposed to go on because, you know, those could be enemy bases or whatever, certain areas to avoid, certain areas to follow, and some safe areas. That's what we wanted to show. And I don't know whether I don't think I have the path showing, image showing the path of the UAV, but what we noticed is the UAV would go all the way here, and then little bit it will go inside these buffers and come back. That's because it didn't have the perfect way of turning a little bit before the buffer. That's about it. Other than that, we didn't see any other issues with this software. So the phase 2 that we'll be demonstrating in future would be on a range, a mountainous range, where you will have unicorns, smaller UAVs flying, or scan eagles against a scan eagle, and there will be a test range manager who will have control over the test framework, and who can stop the test that is running right now. The constraint, this will be much bigger test, close to on 10 by 10 kind of radius, 10 miles by 10 miles kind of radius. And maybe we'll try to experiment with different kind of violations and observe how our autonomy behaves. When the idea is that this is the autonomy that we have, autonomy software that we have been using for various UAVs within APL. Tomorrow, if you want to test some other autonomy system, you should be able to just plug it in and play with that. So the summary of autonomy and T&E perspective has been basically in perspective. Last year's, the main thing is, I think, in terms of our Microsoft project world, the way TRMC director put it is that there is a shift left is happening, which is upfront, people have to think for these autonomous systems, how to test those thoroughly. And it's just going to become more and more complex as the autonomy, purpose of those autonomies or goals of those autonomies are becoming complex. And that's the main key takeaway, I think. That's it. I would like to acknowledge the team, Bob Chalmers, Bob Bamberger, Christine, Dean, Brendan, myself, Bill, and Mike Biggins were the team. There were a lot of couple of subcontractors, 3DM, Boeing, and In situ. There was a lot of support from government flight test centers, both at Aberdeen and Yuma, and the experts in the UAV areas from ONR. That's it. I'm done. Thank you.
I'm fascinated by this notion of testing for safe operation of autonomous things. I'm about to start building them. Did you come up with any generalizable metrics for correct operation and for safe operation of something as complicated as a moving vehicle looking around at the rest of the world?
Yeah, and we started actually, we don't have a metric as such right now, but for a moving vehicle, it was easy that we didn't want it to come this close to the other moving vehicle at that X amount of speed, you know. So if you draw a sphere around a vehicle, you don't want other vehicles to breach that sphere in some way. And the radius of the sphere depends upon the speed of the vehicle and the turning capacity, right? So I think something like that has to be figured out for every kind of, whatever is the autonomy goal that you're trying to achieve. And I just don't have that for all different scenarios, but that's kind of the thinking that went in.
Any other questions? Yes, Joel.
It's actually in response to your question. There was a group at MITRE, and if you email me when I get home, that actually was working on trying, they were a DARPA Grand Challenge team, and then they went on to realize that there wasn't any way to evaluate all the proposed ground vehicle solutions, and they were trying to come up with the guidelines to actually evaluate them fairly. So I got the email contact at home. If you email me, I'll get it to you. And you probably want that.
I would love that too. Thank you.
Other comments? No? Okay. Thank
All
you
right.
very much, Subodh.
Thank you.